Hey, this is video number 2 for Physics 11 for Newton's laws. We're going to look at Newton's second law today. It's all about forces. You can see this tree has been pushed by the wind and has been bent over. It's just the force of air molecules acting against it that has caused it to grow this way. Very important distinction with Newton's second law is that forces make changes. A lot of people say that force makes motion, but it doesn't make motion, it makes a change in motion. So you can be moving with no forces on you at all. That's totally fine. But in order for your motion to change, you need a force to enact that change. So Newton said that if a body is acted upon by net force, it will accelerate. That's a change in motion, not necessarily change in speed. It could be direction as well. But that change in motion is caused by the net force on a body. Body means any kind of thing, and it's directly related to the acceleration and the mass of that body. I always ask my students, if you're in a rocket ship and you're floating, and you have a rhinoceros and a mouse with you, how do you tell that the rhinoceros is more massive than the mouse? And you might think, well, you put them on a scale. But if you're floating out in space, the weight of both of those things is actually zero. The force of gravity on them, which is the weight, remember weight and mass are different things. The weight of anything out in space is zero. The mass, however, does not change. Your mass won't change no matter where you are, if you're out in space or on Jupiter or whatever. Your mass doesn't change. So how do you tell that a rhinoceros is more massive than a mouse if you're floating around out in space? Well, what you do is you hit the rhinoceros. You give it a kick or a punch. And what you'll notice is that the rhinoceros won't move very much. In fact, if you hit a rhinoceros, you'll probably move backwards instead of the rhinoceros going forwards. I don't recommend punching a rhinoceros, by the way. That's not a good thing to do. But if you flick the mouse, he's going to fly off into space. The resistance to force is actually the definition of mass. Your mass is defined by how much you resist force. If you're a big person and somebody pushes you, you're hard to push. If you're little and someone pushes you, you will accelerate more. This is the key to Newton's second law of motion. Now, Newton talks about net force. Why doesn't he just say force? Well, the reason is that any object may have several forces acting on it at the same time. And so right now I'm sitting in a chair, gravity's pulling down on me, the chair is pushing up, and so my net force is zero. That doesn't mean there's no forces acting on me at all. There is. Gravity is pulling down on me. But because the chair is pushing up as well, net force is zero. And that's why I'm not accelerating. If the chair breaks, then the only force on me will be gravity, and I will accelerate. Oops, sorry. So if two forces act on an object, those forces may cancel each other out. If the forces are equal in magnitude and opposite in direction, then there's no net force on the object. Its motion will not change. So here's some nice little deer. They're doing a little fight, and they're pushing against each other. And the one with the greatest force will win. It's funny because we like to think that well, actually, I shouldn't say that. It's not the greatest force that's going to win. It's the greatest acceleration, because each guy wants to change the motion of the other. So the quintessential example of this, and the one I always tell my students, is if there's a bee buzzing around, and it flies over a road, and it's just kind of buzzing around. And a big van comes along. Bees buzz, 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 just going about my business, and the van just, and the bee ends up on the window. On which object is the force greater? You might think, well, the force is greater on the bee, obviously. It gets taken away. But the truth is that the force on the bee and the force on the van is the same. Okay, so every time there's equal and opposing forces, every time there's a force, there's an equal and opposite force in the other direction. And you might think, well, that means the net force is going to be zero. That means nothing's going to move ever. But that's not true. Because even though the forces are always equal, the masses of those two objects are different. And so because the mass of the van is really big, sorry, you do the same side. If the mass of the van is really big, then its acceleration will be really small. If the mass of the bee is really small, the acceleration on it is really high. So its motion gets changed a lot. The question is, does the van slow down when it hits the bee? And the answer is yes, it does. Not very much, but a little bit. If you had a really precise measurement instrument, you would find that the van does slow down a little bit when it hits the bee. It's not very much, because its mass is so much bigger than the bee's. And so this brings us to the mathy part of, here's another example of change. Train 1, car 0. Careful in railroad crossings. Here's the formula for Newton's second law. This is probably the most important formula that you're going to learn in physics in high school. F for force, M for mass, A for acceleration. So it's mass times acceleration that gives you the force, and that's why the force on the van and the bee can be the same. Van has a big mass, small acceleration. The bee has a small mass and a big acceleration. If you multiply those two things together, you'll end up with the same force for the van and for the bee. This is why the acceleration of gravity is the same for all things. Because even though, well, you know what, I'll get into this more when we talk about gravity, but the force of the Earth on you is the same as the force you are exerting on the Earth. You've probably never thought about this before, but the Earth is pulling down on you, but you're also pulling up on the Earth all the time. And what that means is that the force of any object on the Earth is the same as the force of the Earth on that object. And you might think, but that doesn't make sense because, whether you drop a feather or a brick or a rhinoceros or a whale, I don't know why you'd be dropping a whale, or a jumbo jet, they all accelerate down towards the Earth at the same rate. And the reason for that is because all of those masses are negligible compared to the Earth's mass. If you carry that on to a big enough object, if you hold up Mount Everest above the Earth and you let it go, Mount Everest will accelerate it will seem to accelerate a little bit faster. And the reason is because it's going to pull up on the Earth just a little bit. If you hold the moon above the Earth, if you were really strong and you could hold the moon, and you let the moon go, the moon would be pulled with the same force as the Earth is being pulled up. And because the moon's mass is actually, it's a sixth, I think, of the Earth, the Earth would come up to meet it. And so the acceleration of those two things going together would be faster than 9.8. if you held up Jupiter to the moon, or if you held up Jupiter above the Earth, if you're really strong, you let that go, the Earth would actually come up to Jupiter faster than it would come down. And so this acceleration would be much higher than negative 9.8. But because in everyday life, everything we deal with, even jet airliners, those masses are negligible compared to the Earth. The acceleration on all those objects is the same because it's the Earth that's providing that force. Okay. So mass times acceleration gives you your force. Note that the units for force are kilogram meters per second squared. Kind of boring, but mass is in kilograms, acceleration meters per second squared. So kilogram meters per second squared is the unit of force. Because we don't like to say all that, it's kind of a bit of a mouthful. We just called them newtons after Isaac Newton. So if someone asks you what you weigh, you shouldn't say, like, I'm 186 pounds, but I really shouldn't say that. And oftentimes I will say, if someone says, hey, what do you weigh? I'll say, oh, about 800 newtons, something like that. Because if you take your, I don't know if you know your weight in kilograms or pounds, but in kilograms, I'm somewhere around 80 kilograms. And so times that by 10, because my mass is 80 kilograms, the acceleration of gravity is about 10, negative 9.8. So 80 times 10 is I'm about 800 newtons. You can figure out your own weight in newtons for yourself. And that's a good way to tell people that you're a physicist and kind of a nerd. I like being a nerd. Okay, so here's an example. You have a 5 kilogram block pushed to the right along a frictionless track. So there's no friction, with a force of 10 newtons. And you ask, what is its acceleration? Now, I could write this out for you, but I think most of you can probably do this in your head. If we're thinking, okay, force is mass times acceleration, you want to solve for acceleration. So in order to solve for that, you're going to have force divided by mass. And so you have your 10 newtons divided by 5 kilograms, and your acceleration is going to be 2 meters per second squared. If you have a 650 kilogram car accelerating at 4 meters per second squared south, what is the net force acting on the car? I'm just going to open up my calculator here. And if I'm looking for force, I go back to my yep. F equals ma, right? That's my formula. And I'm going to say, so my mass is 650 kilograms. It's already in kilograms. There's no conversion. And I'm going to multiply that by my 4 meters per second squared. And I'm going to get 2,600 newtons. So that would be the force. And you'd have to actually say force is a vector. So you would have to actually technically say 2,600 newtons south. You should include the direction. Okay, pretty simple example, but I was gonna say, yeah, when you have a net force, we can just add those forces. So here you got Tom and Jerry are pushing a 75 kilogram stack of books north along a frictionless ice rink. Tom pushes with 55 newtons, Jerry pushes with 25 newtons. It's pretty good for a mouse, I think. Find the book's acceleration. So you just take those forces and you add them up. So if two people are pushing in the same direction, this is 1D kinematics really, but it's now 1D dynamics because we're working with force, but the concepts are the same. So if they're both pushing in the same direction, you add them up. If they were pushing against each other, you'd have to make one of those forces negative, and then you'd have to, when you add them, they'll become less because they're acting against each other. In this case, they're both going in the same direction. And so 55 plus 25 is 80. So you have 80 newtons divided by 75 kilograms, and it's going to be 1 point something. 80 newtons divided by 75 kilos, 1.066667, and that would be your acceleration. Now, obviously, you will get into two-dimensional cases with forces where you use, you have to use trig and stuff, but we don't do much of that in physics 11. So luckily for you, most of it's in the same line, one-dimensional. So we did our two-dimensional projectiles. Now we're going to back up, and with the forces, we'll go back to one dimension. Okay, one last problem. I think this is the last one. Yeah, we're not going to watch the motorcycle thing. You have here a motorcycle, and we live in this world of friction. So we have 8.5 times 10 to the 3 newtons west. So the W is just west, and times 10 to the 3 just means you move that decimal place back 3 places, and you're going to have 8,500 newtons. So Juno is riding this. Juno is the next student of mine, and she's riding this motorbike, and the bike is pushing west 8,500 newtons. Friction pulls back on it with 1,500 newtons to the east. And so if the bike's mass is 550 kilograms, what is its acceleration? And so we go back to F equals ma. We're looking for a, and so it's F divided by m would give you your acceleration. It's pretty simple concepts, right? The math here is very easy. But you do have to know that these forces are in opposite directions now, as seen by these two arrows here. Bike is pushing forward. I'm backwards here. And friction is pushing against the bike. And so you can't add those numbers together as they are because they're in different directions. So we have to make one negative. I would probably make the friction negative because it's a smaller magnitude. So you have 8,500 minus 1,500. You're going to end up with 7,000 newtons. And if you take your 7,000 newtons and divide by 550, you're going to end up with about 13. I got about 12.7 meters per second squared is what that would be. Okay, so pretty simple examples. The math is pretty simple, but forces do get tricky. You have to be aware of what's going on. But there's the formula, and I'll post some problems for these on the Google Classroom, and you guys can work on those. And then we'll carry on with Newton's laws.